Hello dear friends, welcome to this lecture on ring theory. We are studying ring theory, and earlier we have studied definition of a ring, examples of ring, some special type of ring also we have studied, which are commutative ring, ring with unity. Then we have seen examples of field and integral domain also. In this lecture we shall study what is known as division ring or skew field. First we shall see the definition, and then we shall see its example. Definition I have written here: a ring with unity in which every non-zero element has multiplicative inverse is called a division ring or skew field. The other name for division ring is also a skew field. We have studied earlier field. So what is definition for field? There are three things required in a field: the ring with unity, then commutative ring, and third is every non-zero element must have multiplicative inverse, that is field. Here what is the difference in field and skew field is commutative property is not necessary for division ring. So it may not be commutative, but it must have unit element, and every non-zero element of it must has multiplicative inverse. Then that type of ring is known as division ring. Now we shall consider example of division ring. The ring of real quaternions. This example we shall consider here, discuss here. These are special numbers, real quaternions, and we shall denote the set of real quaternions by a symbol capital Q. Let Q be the set. All symbols or numbers, we may say, we are denoting these by special type of symbols. All symbols of the type, and these we shall write alpha naught, alpha 1 I, alpha 2 j plus alpha 3 k, where alpha naught, alpha 1, alpha 2, alpha 3 are real numbers. This is the set of all symbols of this kind. And what about I, j, k? These are imaginary numbers or quantities where I square is equal to j square is equal to k square is equal to minus 1. And see, real quaternions are extension of complex numbers. Complex numbers we have considered earlier an example of a field, and their numbers we have as alpha plus beta into I, where I square is equal to minus 1. Alpha beta are real. So this is the set of complex numbers denoted by this symbol, and this is extension. Complex numbers have 2 dimensions, and here these quaternions have 4 dimensions. See, 4 parts are there. Alpha naught is real part only, and these are imaginary part, alpha 1, alpha 2, alpha 3. And we will define what is the multiplication operation for addition and multiplication of these type of numbers we shall define, and again in that the multiplication of I, j, k will be defined specially. So this is the set of symbols. Q is the set of symbols of this kind, that is Q, or in short it may be denoted by this notation. Q is alpha naught plus alpha 1 I plus alpha 2 j plus we will not denote it by bar but alpha 3 k, such that alpha naught, alpha 1, alpha 2, alpha 3 are real numbers. So this is the set of these quaternions or symbols of this kind. Now we define addition and multiplication for this. To form a ring we must have set of elements, and again two compositions are to be defined, plus and multiplication dot. Before that we define the two numbers, two such numbers are equal. See, we define the equality as follows. The equality of two numbers. Two such numbers as follows. As see, that means these numbers of this kind, alpha naught plus alpha 1 I plus alpha 2 j plus alpha 3 k is equal to another number beta naught, beta 1 I, beta 2 j, beta 3 k, if and only if alpha I equal to beta j, for I equal to j, and or you can say alpha is equal to beta I takes values 0, 1, 2, 3. So that means alpha naught must be equal to beta naught, alpha 1 must be equal to beta 1, alpha 2 must be equal to beta 2, alpha 3 must be equal to beta 3. Then the two symbols or two numbers in this real quaternions are said to be equal. That is the real parts, and their corresponding imaginary parts must be equal. And also we define addition and multiplication as follows. We define plus operation and multiply, or before that we shall consider two numbers of this type as x and y. Let x is denoted by this symbol alpha naught plus alpha 1 I plus alpha 2 j plus alpha 3 k, and y as beta naught, beta 1 I, beta 2 j, beta 3 k. Now we define plus and multiplication as x plus y is equal to, see, addition of these two, that is alpha naught plus alpha 1 I plus alpha 2 j plus alpha 3 k plus, and the second number, each number has four parts, components of this kind. These are different parts, that is real numbers are different, and beta 2 j plus beta 3 k. The sum of these corresponding components are added, that is alpha naught plus beta naught plus alpha 1 plus beta 1 into I, alpha 2 plus beta 2 into j, and plus alpha 3 plus beta 3 into k. This is the addition of these two numbers. That is simple. Component wise addition is done. And further we defined x into y or x dot y as alpha naught plus alpha 1 I plus alpha 2 j plus alpha 3 k dot, or multiplication beta naught plus beta 1 I plus beta 2 j plus beta 3 k. And here we need the multiplication of these imaginary parts I, j, k, and that is done as like this. Is see, I shall write here the imaginary parts are I, j, k, and we consider a cycle here or a circle, and the elements imaginary numbers we shall consider as I, j, k here, or we may see I, j, k, and this is say clockwise rotation, These are quaternions having 4 parts. We have these, and actually these quaternions are used by mathematician Hamiltonian in its mechanics, classical mechanics, or which is also known as Hamiltonian mechanics, to describe 3 dimension vectors in 3 dimensions, or actually this has 4 dimension, and because this is having 4 components, and therefore these are known as quaternions. And how these imaginary numbers are multiplied, that definition is given as I into I dot I, j dot j, k dot k, and also I dot j dot k is defined to be, these are all are equal to -1. That is one thing. And just like the vectors in 2 dimension and 3 dimension we have, and see where multiplication of these numbers, and we have I dot j, see I dot j, that is equal to k, and but j dot I is that is I dot j is k, but that is minus j dot I, and which is k. Similarly, j dot k, I dot j or j dot k, further j dot k, which is negative of k dot j, and j dot k is defined to be I. And next is k dot I, which is, you see, k dot I is defined to be j, but that is minus I dot k, and that is j. So this is the multiplication for these numbers, and therefore actually what we have is these are the quaternions, which may be denoted as see, we can form these 8 elements as plus minus 1 plus minus I plus minus j plus minus k forms a non-abelian group under multiplication, under this under the multiplication. What is the multiplication? And that is defined above. This type of multiplication is defined between these 3 numbers or imaginary numbers, and using these this multiplication we have to multiply, or we have to define the multiplication of x and y, these 2 symbols, and that can be done now. See, this is we have alpha naught beta naught, real part, that is the same, and now you see alpha 1 into beta 1, I dot I is -1, so that will be negative, minus alpha 1 beta 1, and similarly j dot j is -1, so it is alpha 2 beta 2, negative alpha 2 beta 2, and similarly k dot k is -1, so alpha 3 beta 3 is negative, alpha 3 beta 3, so that is real part. Plus now we can consider the component of I. See, the component of I can be considered like this, alpha naught beta 1 into I. So I collect here the component alpha naught beta 1, and then I into alpha naught. So this is done, that is alpha 1 I into beta naught, alpha 1 beta naught plus alpha 1 beta naught, alpha 1 beta naught, and again component of I is here, you see, that is j dot k. J dot k means this j and k, and that is alpha 2 beta 3 plus alpha 2 beta 3. And now what about this is minus I, k dot j is minus I, k dot j alpha 3 beta 2, and that is negative alpha 3 beta 2. You may check according, this is important definition of multiplication of these imaginary numbers, and using this definition we have defined the multiplication of 2 symbols x and y. So this is the component of I, plus now j. So what about j component? We can see, so this is alpha naught into beta 2, alpha naught beta 2 j, and now j components are obtained by k into I. So this is k and I, that is alpha 3 beta 1 plus alpha 3 beta 1, and again j component is see, this is I j k, yes, the j dot k is I, we have defined like this, I dot j is k, j dot k is I, etc. That is right. Here from this we can get this, and yes, I think it is correct. Alpha naught beta 2 alpha 3 beta 1. See, alpha naught k j components we are collecting, and k dot I here alpha 3 beta 1, that is right. But there is earlier j component which is alpha naught beta 2, and this is beta naught alpha 2, beta naught alpha 2. So I shall write that first, alpha 2 beta naught, alpha 2 and beta naught plus alpha 2 beta naught. And now further we will consider according to this k into I, k into I, this is k and this is I. So alpha 3 beta 1 plus alpha 3 beta 1, and now I into k with negative, I into k, that is alpha 1 beta 3 minus alpha 1 beta 3, and this is the component of j. You see, and further the last component of k is there. See now how to define the component of k, and alpha naught beta 3, alpha naught beta 3 plus it must be now alpha 3 beta naught. These are interchanging, you see, alpha 3 beta naught, that is component, and next is plus, see, k component I j, I into j, alpha 1 beta 1, I into j, alpha 1 beta 2, alpha 1 beta 2 minus, and now this is j into I with negative, j into I alpha 2 beta 1, alpha 2 beta 1. So this is the multiplication we have defined with the help of multiplication of these quaternions I, j, k, and our imaginary numbers. Now you may see here it gets, this is the real part, alpha naught beta naught minus alpha 1 beta 1, etc. This is alpha naught beta 1 alpha 1 beta naught. So these are interchanged. Here also these are interchanged, last is negative. Alpha 2 beta 3, this 3 suffix comes to alpha and 2 suffix comes to beta. Likewise here also these are interchanged, 2 0 to 2 0, 3 1 1 3, and so on. But according to this we have to write the multiplication of these two symbols or numbers x and y of real quaternions. So in this way we have defined addition and multiplication. Now we shall check, once these are understood clearly, what are the elements we have, the elements of this type x, and how the equality is defined. If the corresponding parts are equal, alpha I is equal to beta I, then the two are equal. And see, we have defined the equality. So if and only if x is equal to y, see, these are equal if and only if this, that means alpha I is equal to beta I, that is x is equal to y. Here this is the condition. Now the addition is defined as corresponding components are added, and here multiplication is defined with the help of these order. That the rotation is important. In clockwise rotation the multiplication is taken to be next imaginary number positive. I dot j is k. So I have denoted this rotation clockwise. I dot j is k, j dot k is I, k dot I is j. And if you reverse it, j dot I in this sense, then it is negative k. J dot I, see, j dot I is minus k, like this. And I into I, j into j, k into k, or I, j, k is equal to minus 1. That is the definition for multiplication of these three imaginary numbers. And with the help of these composition x plus y and x multiplication y plus and multiplication, we shall check whether this is a ring or not. And it is now easy to check this plus is abelian group. So because x plus y, it is closed. X plus y is this number, and this is again in the set of real quaternions, because it is having four components, real, and these three parts are imaginary, and therefore this belongs to Q, and multiplication is closed. It is commutative. X plus y is same as y plus x, because only the symbols will be interchanged, and these are addition of real numbers, and that is commutative. So this addition is associative. This will be addition of real parts, and this is associative. So further, what about the zero element of this? Zero element of this we shall consider as, see, 0 is equal to 0 plus 0i plus 0j plus 0k is the zero element. Of Q under multiplication and under addition. Zero element is an identity for addition. And what about the additive inverse? If x is this, then negative of x, negative x, which is minus alpha naught minus alpha 1 I minus alpha 2 j minus alpha 3 k, is the additive inverse. Additive inverse of x, and thus the inverse exists with respect to addition, and thus it forms an abelian group under addition. Now next property is multiplication is closed. Now you see, this is the multiplication x into I, and it has again four parts: real part, then I component, j component, k component, and therefore it belongs to Q, and thus the multiplication is closed. And multiplication is also associative. That means we have here as x into y, or x into y into z is equal to x into y into z. So this can be easily checked as like this using these multiplication, and therefore multiplication is associative. Further, see, this multiplication is distributive over addition, and that property is x into y plus z is equal to x into y plus x into, or x multiplied by z, and this is a left distributive law. Also we can check this as y plus z. Z, what is z? Z is the symbol of the same kind we can consider here as z is equal to gamma naught gamma 1 I plus gamma 2 j plus gamma 3 k, x, y, z, and for this we can check associative property and distributive property for addition as well as for multiplication. Here for addition also associativity holds, and this is y into x plus z into x. Thus the distributive laws also hold. And one more thing is ring with unity, we have said. This is ring with unity. And what is the unit element for this? This is the zero element we have written. So unit element is, and we have 1 is equal to 1 plus 0i 0j plus 0k is the unit element, and it can be checked easily. It satisfies the property x into 1 is equal to x also, and 1 into x is x, or x into 1 is x again, and is the unit element of Q. So thus this forms a ring. We have checked all the properties, 8 axioms of ring, then this additional axiom, that is it has a unit element. So therefore this is a ring with unity. Now what is remaining to check is it has multiplicative inverse. Every non-zero element has multiplicative inverse. So let this be x, we shall consider as the element of this. Let x be non-zero element. Be a non-zero element, and if it is a non-zero element, not all alpha naught, alpha 1, alpha 2, alpha 3 are not all 0, at least one is not 0, and therefore we have then alpha naught square plus alpha 1 square plus alpha 2 square plus their sum of squares is not equal to 0. And now what we shall do is define, let another symbol we shall consider as beta. Beta is equal to alpha naught square plus alpha 1 square plus alpha 2 square plus alpha 3 square, and this is taken as beta, so which is not equal to 0. Now we consider a symbol, another number in Q, as we shall denote it by again y. Let further y is equal to, say alpha naught divided by beta minus alpha 1 divided by beta into I, minus first positive and rest negative parts, alpha 2 divided by beta j, alpha 3 divided by beta k. See, this belongs to Q. Again it is of the same type, 4 parts components, real, and these I, j, k are imaginary, 3 imaginary parts, and therefore it is a symbol or number in quaternions, set of real quaternions. So this is y belongs to k, and this y belongs to Q. Now what about x into y? X into y we shall see. X into y means product of these two. See, I shall write here now x into y is what is x? X is here alpha naught plus alpha 1 I, alpha 2 j plus alpha 3 k, and this is y alpha naught divided by beta minus alpha 1 divided by beta into I minus alpha 2 divided by beta into j minus alpha 3 divided by beta into k, and their product is defined just as earlier. We have done x into y. Now here y is different, therefore this product will be different, and you see this is a real part will be alpha naught into alpha naught divided by beta, and the see quotient is common, so I shall write that quotient beta as common. And what will be the numerator? Alpha naught into alpha naught square, and you see alpha 1 into alpha 1 in I into I is minus 1, and this minus 1 and this minus becomes plus, so alpha 1 square plus alpha 1 square. Similarly alpha 2 into alpha 2 and j into j is minus 1, so that minus 1 and this minus sign becomes plus alpha 2 square, and similarly alpha 3 square. So this is the real part, and what is the part of I? Now see alpha 1 into alpha naught, and this beta is common denominator, so alpha 1 alpha naught, and that is the component of I, alpha 1 alpha naught, and again the component of I is here alpha naught alpha 1 with negative sign, alpha naught alpha 1. And similarly the component of I is obtained from this jk. See, jk, that is minus alpha 2 alpha 3. And again the component of I is negative kj, and its negative means it becomes positive, plus alpha 3 alpha 2, and that is I component. And what about j component? See, I shall write here j component, and j component is alpha 2 alpha naught divided by beta. So alpha 2 alpha naught and divided by beta is common, and you see alpha 2 alpha naught j component now, that is alpha naught alpha 2 with negative sign minus alpha naught alpha 2 with negative sign. And again j components are obtained by this k into I, that is negative or yes, minus alpha 3 alpha 1 minus alpha 3 alpha 1, j component we are considering. I into k with negative sign, that becomes positive, and that is alpha 1 alpha 3. And lastly the component of k. See, the component of k, alpha naught k component, alpha 3 alpha naught divided by beta, alpha 3 alpha naught. And further you see k component, that is minus alpha 3 alpha naught minus alpha naught alpha 3. And k components are obtained I into j, it is here, alpha 1 alpha 2 negative minus alpha 1 alpha 2, and j into I, that is negative means it becomes positive, plus alpha 2 alpha 1. Now we may see. So what about the first part, alpha naught square plus alpha 1 square etc., that is you see beta divided by beta is 1. So this is equal to 1. So I shall now rub it, and thus the multiplication is obtained according to this, considering the circle and cyclic rotation. So this is 1. This is beta by definition. Beta divided by beta is 1. And what about the remaining? Alpha 1 alpha naught, this is negative of each other, cancel, and these are also negative of each other, cancel, means it's 0. 0 divided by beta is 0, plus 0 into I. Similarly you see this is 0. These are negative of each other, 0 j, and this is also 0 k. And what is this? This is unit element. This is equal to 1, unit element, and thus x dot y is unit element, and therefore y is multiplicative inverse of x. Therefore x and y are multiplicative inverses. Similarly we can check y into x. Inverses of each other. Also y into x is equal to 1, and thus what we wanted to prove is every non-zero element has multiplicative inverse. We have considered x non-zero element, and we have shown that y, which is defined like this, is multiplicative inverse of x, and thus this forms a division ring, or which is known as skew field. So this is a special example of division ring, which is known as ring of real quaternions. So thus in this lecture we have studied what is the meaning of division ring with unity in which every non-zero element has multiplicative inverse, which is also known as skew field, and we have studied one example of real quaternions as a division ring, example of division ring. So thank you for watching this lecture. The remaining part we will continue in our next lecture. Thank you.